So, okay, let me start recalling what we did last time. So last time, we proved the following. So we proved that if we have R as regular, okay, then we may look at the Frobenius action on local cohomology. Right? So what is this? This is literally, I guess by a use of notation, well, so this is a functor, right? So I can apply it to any map. So I'm just going to apply it to Frobenius. Okay? And so certainly this map is not R linear. It is P linear, right? So to make it R linear, I should have to put something here. Okay? This map here is R linear, but I'm just going to forget about it because of the tradition. It's more like to think about it as an operator on the module. So what happens is that if you have an element here, that's denoted by eta, you multiply by an element of R, well, it's not like this, but it's like this. Okay, it's P linear. Talk about it. Okay, so we have this. So we look at that, and so we prove. The other day we proved that for all C, let me put R circ. This just means avoiding all minimal primes. Recall that geometrically this means that when I localize at C, in that open I'm going to contain all the minimal primes of R as points. So when I localize at C, I preserve all the irreducible components of R. I don't ignore any of them. So we proved that for all such C, there exists E sufficiently large such that the map given by iterating E times and multiplying by C. This is an additive endomorphism of this guy, right? We prove that this is splits. And so it's injective. Okay. So, and how does that imply that this is Cohen-Macaulay? Well, this implies that this is Cohen-Macaulay, or is Cm, because there exists C in R0 such that C kills every single one of this as soon as I is less than the dimension of R. Right? So if there is a C killing this local cohomology modules, and you have this property, then that's going to force them to be 0. Right? So then we have that these guys are 0. Which is what needs to be Cohen-Macaulay. Okay? But here you see that R of regular implies two things, right? First of all, R is Cohen-Macaulay, but also you have this condition here that for all C in R0 there exists E sufficiently large such that the action of this operator on the top block of homology, right, is split and so injected. Okay. And so if you look at the literature, these two things together are often bundled up in the notion of F-rationality. Okay? F-rationality means these two things, right? Cohen-Macaulay plus this action of the Bingham log of homology. Okay? So EKA F-rational. So, but actually, at this point, you should be able to prove this better version of this. So, theorem that you can prove as an exercise is that if you take, what do I need here? Do you need logo for this? Well, let me do the local case. If you have Cohen-Macaulay, plus normal. Okay. Let me take this and let me assume that it has a Cartier operator. Yeah, so in that case, then you have the following characterization to R if a regular, if and only if, well, let me say normal domain 2. So in that case, instead of writing R cert, I just can say that C is different from 0. So if you have such a thing, then there exists E sufficiently large such that the Cartier operator times C, you look at the order, how it changes. Now you act first by C, and then you act by the Cartier operator. Splits. Okay. That follows it. That's a dual argument. That, like it's just taking Max's duality and apply to that. Okay. So you can do this as an exercise. So actually, in principle, you already did this exercise for F injectivity, right? The irregularity part has this. First of all, you have to take sufficiently large powers, and you have to do this twist by C. Okay. So, but yeah, you see, it's a very strong thing. It's stronger than surjectivity. So, okay, so now let's talk about the regularity. Let me recall what the definition of a rationality was, right? So this wasn't our definition. You remember what the definition was? We said that if we have R with Cartier operator, right? So this is a rational if and only if by definition the pair omega R kappa, if this Cartier module is a regular, right? That was the definition. The rationality is simply the irregularity of the Cartier module, right? So you see that in principle, so here, like in F-singularity theory, there are only two notions, so purity and irregularity. You see here how rationality is just that. So we had this a while ago as a definition. Okay, so let's try to get to this, okay? Or to get a criterion like that for a rationality. So the good thing is that at this point, we have worked so far that all these observations are very simple. You can do them as an exercise, and you should, to make sure that you follow what's going on. Here. Let's try to apply matrix duality to this. So let me do this theorem. This proof is an exercise for you. Let me take a Cohen-Macaulay thing of finite, that's very important. So notice that for that definition of a rationality, finiteness is necessary, right? Like we only talk about Cartier operators in the finite case, right? Remember that the Cartier operator comes from duality for Frobenius. So to apply that duality, you need to have a finiteness for sure. So let's say you have something called Macaulay, and with Cartier operator, kappa. So okay, right? This is needed just to talk about this, right? This has implicit the fact that R has to be a quotient of a Lorentzian ring and so on. So let's take that. And let's see what matrix duality does to you. So then, if you take a Cartier submodule okay, so what can you do out of it? You know that the quotient of this is a Cartier submodule, right? Cartier modules are an abelian category, so all the quotients in these basic operations respect the structure. So you can take the matrix dual, right, of omega R M. And where does this live? This is going to be a submodule of R. Well, what type of submodule is this by matrix duality? Remember that when you apply matrix duality to the Cartier operator, what did you get? You get the Frobenius action on local cohomology. Remember? So that's a very important point here. Matrix dual of K equals F on this guy. Right? And so when you do this, what you get is a F submodule. So this is an F submodule. And so notice that so the point is that matrix duality is a contravariant functor. So co-kernels go to kernels. If I apply matrix duality to M, well, M is going to be the co-kernel of this quotient. Sorry, well, it's going to be the co-kernel of this inclusion, right? So this is why I have to take a submodule, take the quotient and apply matrix duality to get a substructure, right? Because it is a contravariant functor. Does that make sense? So you get this F submodule. In a sense, this is an observation we have made before. So that's pretty okay. And what do you think is the converse here? If you start with a submodule, let me call it N. At submodule. And then I look at what? Oh, there's a typo here. So if I apply matrix duality to this, the matrix dual of this is going to be omega r, right? So it's contravariant, so this gets reversed. Okay? And it's going to be surjective actually, because this is injective. And so it has a kernel. The kernel of that is a Cartier submodule of omega r. Okay, so and point C is that these are inverses of one another. So these are inverses of one another. Okay, so Cartier substructures of omega are the same as Cartier F substructures of topological homology by matrix duality. Okay, so well, the conclusion here, well, maybe I'm gonna do a different order than is here in the notes. In particular, R is irrational. Well, R is irrational if omega R is a simple Cartier module. So the conclusion is, if and only if this guy here is a simple F module, it has no substructures other than 0 in itself. Irrationality by definition is the irregularity of omega, which means that omega has no substructures other than 0 in itself. Okay, that's what you get. And I guess E is what happens in the Gorenstein case. So if R is further Gorenstein, I'm gonna let you just want to say a word. Let you use this bijection to write down a bijection between the compatible ideals of R, right? Because now omega R becomes R in the Gorenstein case, And Cartier substructures are going to be just these things, or equivalently quotient like this. Well, no, these are going to be the substructures, and then the matrix dual of the quotients are going to be the F substructures of top local homology. So write down a bijection between this and let me say F submodules of top local homology. Okay. And so, for example, here, if you have a compatible ideal, you send it to the matrix dual of R modulo A. And the inverse would be to take like the submodules here and take the matrix dual of its annihilator. No, the annihilator of its matrix dual. Okay. So that's a very common thing. Any questions with that? Do you buy all this? And in principle, it should be it's simple to prove right now. So the way I look at this is that for me, a rationality conceptually is the irregularity of the canonical module. I think that's the right conceptual way to think about it. But in practice, it's way better to look at this when you have to write down proofs. Because local cohomology comes with a lot of tools. Cohomology, right? So that's the business here. And so look at this. So this is what I mean that and rationality is really nice. So I guess theorem, which is an exercise for you, is to take a beautiful Cohen-Macaulay local ring, okay, with Cartier operator, and prove that R is a rational if and only if. Let me take it to be a domain, to be honest. Domain for all z different from 0 in R, there is E bigger than 0 such that the Cartier operator times C is surjective. Actually, I think I forgot to put here some exercise. You notice that here I didn't put normal, but an irrational ring is necessarily normal exercise. If rationality implies normal. So then we can have the comparison here, right? Because even if I didn't put it here, it's a hypothesis. So maybe the exercise comes here. Okay. So and now you are comparing, apples with apples. If you have a local Cohen-Macaulay normal domain, what is the difference between F rationality and irregularity? Literally, just the difference between splitness and surjectivity. Yeah. That's it. Irregularity is way stronger because you see, it forces this operator to split. Whereas F rationality is just about it surjecting. But yeah, that's a huge difference in practice, right? Homological algebra, you see, it's definitely a big deal. And so that's it. That's what I want to say. I think this is the best way to think about it. So first of all, both notions imply Cohen-Macaulay normality, which is the minimum base, right? For to talk about F-singularity. Sorry, to talk about singularities in general. You really want to have normality and Cohen-Macaulayness at the bare minimum, and then you have these two notions, a rationality and a regularity, which you can understand as notions about the Cartier operator. Okay? And one gives you splitness, and the other one surjectivity. And when is projectivity and splitness the exact same notion for what type of modules? What would be a property for omega that would guarantee that surjectivity and splitness are the exact same thing? When it is a projective module. Right? Projective means that surjections are the same thing as splitness, as splittings. Right? Splitness implies surjectivity, right? For sure. Because splitness means that there exists a section that will force things to be surjective. And when you have a projective module here, it means exactly that for those modules, projectivity and splitness are the same thing. And when is omega projective? When R is Gordian. Exactly. Well, actually, that's only the case when you have a Cohen-Macaulay ring. In general, when you have a ring that is not necessarily Cohen-Macaulay, but omega is projective, you call it quasi-garnishing. So actually, what I'm about to say is it's true for quasi-garnishing things. Well, we haven't talked much about it, so I won't get into that. So the corollary is that this is it. Corollary of regular implies a rational, and the converse holds if you put garnishing as your hypothesis. Okay. It's very nice, isn't it? Now I hope you fully understand well how this implication works. And generally, this is like the main takeaway of this course. I also hope that you appreciate that why irrationality, in a sense, is it's sometimes better behaved. Because subjectivity is gonna be, it's a better homological notion. Like splitness is too much to ask for, right? It's just too much, in a sense. So yeah, so this is way stronger, but you cannot expect it to preserve it if you do certain operations and so on. So yeah, you got this. So you will see sometimes people do it in the quasi-garnishing case. And so, well, just to complete the picture, also we have the pure, right? This implies a regular. I guess technically speaking, for me to say this, I need to assume infiniteness, right? Because a purity doesn't imply infiniteness, and irregularity, as far as we have discussed in this course, only makes sense in the infinite case. Okay. So technically speaking, I should say that. But I guess for now that has been sort of a hypothesis everywhere. This implies F injective, right? And F injective implies a rational, because actually F injectivity, if you think about it, is what irrationality means, but for C equals 1. Right? F injective means that here you have for all C. F injective just means for C equals 1. Okay, and so this implies that. And we also saw that this goes like this in the coherential case. These two notions here implies normal. That's very good to know. And these two things here implies weakly normal. So yeah, this is the picture of F-singularities. At least the 4 main notions. And at this point, then you get into study them. That will be for a second course. But yeah. Something we haven't talked much about is the notion of how is it a splinter? But actually, I meant to write down a proof. I got lazy because it's not easy. You know, like I told you that this is a big open problem, right? That you should try to think about it from time to time in your free time. When you're taking a plane or so, you should think about that. But actually, what is true is that this is true. This is question mark. This is exclamation mark. But I didn't prepare a proof, so maybe at some point when I have some free time. Splinters are irrational, but expect to be irregular. So you would see that this conjecture is true in the Gorenstein case. So this is true in the Gorenstein case. Even in the Q-Gorenstein case. Okay, but something crazy is that irrationality doesn't imply irregularity in the Q-Gorenstein case. So yeah, so that's the picture.
I'm sorry. Yeah. Irregularity imply the pureness, like the arrow is in these backwards.
Yeah. Yeah, you're right. Yeah. Yeah, of course. And definitely, yeah. I said something very stupid. Yeah. Yeah, I think I'm used to writing this on top. So you may ask if regularity is the intersection of irrationality and empiricity. I asked that myself, but that's not true. So if you put the intersection here, well, of course, irregularity implies that. But there are examples of things that are pure and irrational that don't imply irregularity. Okay. And the gap is huge. And yes, as I told you, the idea is in general to prove that the singularities are as wonderful as they can be. And the belief in general, the faith of the field is that these are the best type of singularities to do the math. Okay, this is the minimum that you can ask for, in at least a positive characteristic, to be able to do things. You may have heard that they are analogous to the singularities of the minimum model programming, right? There is a similar picture, and those are the minimum type of singularities you can have, and you have to allow to have to do things. So it's a similar belief.
And the next clear thing besides being irregular, is it like plainly regularities?
I think so, yeah. Yeah. But yeah, so the point is like regularity is not good enough. So the point is like you can do so many things that are so basic that destroy regularity. But in practices, what happens is that that tends to deform to some of this, especially irregularity. Okay. So in a sense, what happens in practice is that irregularity is the regularity. Is the notion of irregularity. The point is that irregularity is the notion of regularity. Like it's like with regularity we got it wrong. And irregularity is like this bigger but better behaved notion of regularity. Is regularity as far as for me is concerned, so to speak. That's intuition. But you could argue that the same about irrationality. You could say that irrationality is actually the good one. But it's sometimes too weak. And so that's, I don't know. Depends what you want to do, really. Yeah. So I guess in practice, what you start doing is like you have this as your hypothesis, and then you start to do things. And then like what you do may break the regularity, maybe you end up here or you end up here. And then you have to still do what you can do and come back. That's the game sometimes. Yeah, so the hypothesis you may want to have is a regularity, but you may want to have the freedom to play with the other notions too in the middle of your proofs and your mathematics. Okay. Yeah, so there are a billion of open problems that we could talk about and so on. I wanted to say more about F-rationality, but I did, we just have half an hour, so I thought it would be better to talk about F-signature, because it would be kind of sad not to talk about it, because that's the other way to think about F-rationality, sorry, F-regularity. Before getting into that, so yeah, if you look at this thing here, for example, I just wanted to say one more thing. Based on thinking about F-rationality as the regularity of the canonical module, and it is because if you think about it, the very basic stuff are very easy to see. Like for example, the rational locus is open, because it's just about test idea localized, not just a test module. But if you look at this perspective, that's kind of hard. Actually, it's not so easy. It's not impossible, but it's an argument for sure. So yeah, so sometimes people say, okay, you know, for this you need the finiteness. For this you don't need anything. Frobenius can be as wild as possible. And so you may take this as your definition of F-rationality when you are dealing with very general rings, specifically when they're not defined. You can do that, and people do that. And then all your proofs become very difficult. But still, that's a thing, that's a path we could have taken after this, which I was thinking to do, but since we don't have much more time, let's just leave it there. So for the final minutes I have in this course, so I would like to briefly talk about F-signature. I put all the details in the notes. So today we're just gonna go quickly through it, skipping all the proofs essentially, and then I'll let you read the details. Okay. So the F-signature is this pretty thing. One sec. Okay. So section 9.1. Signature. By the way, there is something called dual signature, which would be the F-signature of the canonical module, and therefore it measures F-rationality. F-signature measures F-regularity. But the dual signature is a much more difficult object, so we won't get into that. So how quickly do I want to go through all this? It's a lot of details. Let's go through it. So okay, so let's set a. It's definitely a local thing. So we're going to take an integral domain. Okay. Let's make general remarks. Let's take M to be the finally generated R module. And so there are many types of ranks we can attach to this. So the first one is the so-called generic rank. I'm going to denote it by nu. But we could have the generic rank. Maybe this is a better notation. Generic rank of M. It's simply, well, what you do is that you do this base change, right? And then you get a K vector space, where K is the field of fractions of R. I'm just localizing M at the 0 idea, right? It's just that, nothing scary. And then you look at this dimension. That's the generic rank. Okay? It is the rank of M at the generic point of R. So there is another notion of rank we have seen already, which is the residual rank, which is the minimal number of generators of M. It's the complete opposite, right? So here I'm looking at the generic point, and now remember that my Nakayama lemma, like we could also go and do this, right? We can take the dimension over K of M tensor K. Right? The complete extreme. And by Nakayama, this is what? This is the minimum number of generators. Okay. In other words, it's the minimum of all the n's such that there exists an exact sequence like this. Right? So so this is very cool because out of this is a very cool exercise. This is one of my favorite parts ever. M is free. So something you should notice right away is that one of them is way bigger than the other one. Well, in principle, what is it? Nu is always smaller than mu. In general, this function here, or sorry, this comparison, well, actually, they are the same type of thing, right? They just measure rank at every residue, at every possible residue field at the prime idea, right? It's just that we go from the generic point to the close point, to the most special point. And so the more generic your point is, the smaller this rank is going to be. So that means it's a semi-continuous, upper semi-continuous function on the spectrum of R, and so on. So you get this, okay? In general, right? And so what I'm saying is that M is free exactly when you get equality here. And then M will be free of that rank. Okay? So how different these two things are tells you about how free this module is. So you can see that based on Frobenius, this is a good thing to consider. Going into that is going to take you to the Hilbert-Booth multiplicity that we are not doing here. So the next type of rank I want to talk about is the free rank. So free rank, maybe I could call it like this, but just be consistent with this Greek letter notation. The free rank of M, I guess. I'm gonna call it eta. And this is gonna be a maximum. It's kind of dual to this. So here's the minimum of that. I'm gonna take the maximum of all the n's such that there exists and there is an exact sequence like this. Okay. So why is this called the free rank? It's because this is a projective module, right? And so writing this is the same thing as saying that N has this as a direct sum. So this is literally the rank of the largest, the largest rank of a free module that you can split out n. Okay. So, and so in general, if you compare all these things, you're going to have that the free rank is the smallest one. The free rank is smaller than the generic rank, which is smaller than the minimum number of generators. That's a comparison between these three equalities. So, for example, I'm going to let you do some exercise in the notes. You may want to know what it means that this is equality here. This is equality, actually, if and only if. Well, I guess, so equality here plus m being torsion free is equivalent to m being free. And if you consider the whole thing to be a whole equality, so these two things are equal if and only if m is free actually. But this one is not too strong. To get freeness, you need torsion freeness. List. So, any questions with this type of numbers? And this is the key. This is the key to see how they are good things together and to see that the signature exists, which I haven't defined yet. I'm going to do in a second. So exercise is the following subadditivity formula. So suppose that you have an exact sequence like this. And the point is that this thing here is not subadditivity as opposed to these ones, of these two which are, okay? But you have the following. So you can say that the free rank of the co-kernel is less than the free rank of m, which is less than the free rank of m prime. And here, your dream is to put eta of m double prime, right, at the very least, but it's not the case. So what you get is here mu. This is a tricky one. Okay. That's a tricky argument, but I put a hint here in the notes so you can look it up. Okay. So what do we want to do? You see that these numbers, right, tells you how free a module is. So the point is to apply that to who? To the Frobenius force forward of R, right? So remember, R is regular if and only if this thing here is free. That's good. And so we may want to come here and say, okay, I can try to compute the free rank of Frobenius. Which is torsion free, right? Because R is a domain. So this is torsion free. And so I can compare it to its generic rank. Right? This is always bigger than 0. So even better, I can look at the quotient. Free rank versus generic rank. Okay? And this is 1 if and only if R is regular. So if I had a regular ring, these quotients here are always 1. That's another way to express Kunz's theorem. It will be a constant sequence of 1s. Very boring. Okay, so this is the conceptual way to think about these ratios. I just want to make a remark here with what is the connection with the Cartier core or the splitting prime, and also because that's usually a very useful way to deal with these other ratios. So first of all, I would like to compute this number. Okay, because one can do that very explicitly. So this is the next page next here. So there's a typo here. Oh no, there is no typo. Okay. So remember that we had that local ring with field of fraction scale. So let's look at this number for a second. By definition, this number is this, and what you're looking for is at the degree of this field extension. You guys agree? Because generically, this module, that's what I'm saying here, this module generically is just this, because Frobenius will deal with localizations, right? And this thing here is just that. Is the dimension of this is a K-vector space. So, but you know from also from basic field theory that what you do that you look at this one and then you raise to the e because you have a chain of field extension, right? And degree decomposes multiplicatively like this. Where I guess the point here is that this thing here looks like this degree here looks like p to the something natural number. So I guess a way to say that is that the log base p of this number is a natural number. I.e., this thing here equals p to the something that is a natural number. Okay. Just a general remark. In general, we're going to have the following. This is a more or less non-trivial proof, but it's in the notes, so you can read it. It's the first step here. So in fact, proposition, I can tell you what that number is. This is going to be what you get at the residue field level This is another natural number, okay? Plus dimension of R. So this, and remember, this is essentially nu. Well, kind of like nu would be p to the that. Okay.
What's the difference between the left-hand side and the right-hand side?
Left-hand side right here. Equality. Well,
But you added something, right?
dimension of R.
Isn't it the same thing, the like extension? Yeah. I mean, the degree of the K1 over B and K on the right-hand side is K1 over B.
This is the residue field.
Oh.
And this is the field of fractions. Yeah.
Yeah, it was the same K.
Yeah, you know, it's, no, this is little k,
Okay.
this is big K, sorry. Maybe the notation is kind of confusing. I guess another way to say this is that I'm just telling you in the face, you know, that this number here, the generic rank of this object, is easy to compute, and all you have to do is to compute what is going on in the residue field, which often is not even there because the residue field is often like perfect. So you will have to take this is the E and multiply by Q the dimension of R. That's the growth of this number. And you can find the proof here and everything. Okay. On the other hand, let me describe more explicitly how to compute the free rank. On the other hand, let's look at eta. And well, I haven't said this, so the point is that there is a very specific way or a very explicit way to calculate this. So let me do it in general so that it is clear what I'm going to write down here. So to compute this, what you can do is the following. So this is going to be equal to the dimension of the following vector space. And here you can replace dimension over k by length of module. So you take m, you're going to take the quotient of m by something that in the notes I'm denoted like this. And so this thing, it's going to be a certain transpose of m. I have this in place. And so what you do is you look at the elements of m. So this is a submodule of m, and you're going to hit these elements. So this is the maximal ideal by phi, and phi belongs to the dual of m. So this transpose of m is going to be by definition the elements of m that whenever you hit them by phi, where phi is in there, it lands inside the maximal ideal. So if you think about it, these are the elements of m that never gives you a free sum of m, right? And so if you kill them, you get a modulo of final length, and the dimension of that thing is this range. Okay, so actually the point is, well, it should be clear that this is a modulo of n. It's right there in the definition. But you can see that it's gonna contain this guy, right? Because if you hit phi, if you hit this module by phi, well, the n is gonna go outside, and automatically you're gonna land inside n, the maximum idea, right? And so that means that this quotient here, right? It's a module of this by this, which is a K vector space. So this thing makes sense. You see? Okay? And this is true in general. It's an exercise in the notes that you should try to do when you get a chance. Okay? So then you go and look at that, and you apply this, right? And so you're going to have, okay, I'm going to take the dimension. And again, here I can replace dimension by length. Remember that final length modules are the same as K modules. And length becomes dimension, and all that. So here, yeah, so you say, okay, I'm going to take my Frobenius push forward, and I'm going to look at what I have here. What would this be? Well, it turns out that by definition, this is just this thing. I'm not sure if I called this IE differently before, but what are these IEs? These are the elements of R, such that whenever I hit them by phi, they live in M for all phi in here. Probably I used some sort of transposition thing to denote this. It wasn't. I guess the notation we had before is that this is the intersection of M phi, where phi belongs to CE, or something like this. And if we intersect over all the E's, that's going to give us the Cauchy-Korov M, or beta of M, or the splitting prime. Okay? So I'm just looking at every specific one, or every single one of them. Okay? So that's what goes here. But then I can remove the Frobenius push forward here, which I'm going to let you do as an exercise. So by basic algebra, this is going to be this. Then here I can take this eraser. And so here I'm going to be able to take dimension of the quotient of R by these IEs. So, yeah. And so what is the punchline? Then when you compare, okay, look at this. So when you compare the free rank of this thing versus its generic rank, well, now these two things are going to cancel each other. And you get dimension or co-length, that's the other name this has. This is called the co-length of IE. And you divide by Q, dimension of R. So this is how you think about it. And this is how you actually deal with it. How do you do calculation? You know, you calculate it. Okay. This is rich, you know, like you can think about it, it tells you things, conceptually speaking, but it's hard to do things with it. So very often people end up working with that type of things. So, okay. But this also makes sense because you actually know that the intersection of all the i's if you this notion of a regularity, right? So, yeah, remember, very cool. I guess beta of the maximal ideal is the split. It's called the splitting prime actually. Let's look at case. If the splitting prime just turns out to be the intersection of all these i's. So this is the pure case actually. These i's will form a nested sequence of ideals. They just get deeper and deeper and deeper. The more you go, out with the e. And so this intersection is getting very, very small. Okay, but it may not be zero. And so actually, remember, R is a regular if and only if what? What happened to this intersection? It is zero, right? This ideal here is the largest compatible ideal of R. Now it's a regular if and only if it is zero. And so probably that's suggesting you that these numbers better get big as e grows. So hopefully as big as this one. Okay, so I guess I'm getting hungry. So let's finish for today with a few theorems. So what people do is then to define it's here the following. So they say, okay, I'm going to have this ratio here. But actually, these numbers are called, I guess either one are called splitting numbers. So let me call them AE. Let me call this AE. It's actually a common name for them. So let me take AE of R. I'm going to divide by Q dimension of R. 1. And so I'm going to take the limit when E goes to infinity. So in practice, actually, this number is often a polynomial in Q of dimension bin. And you're looking for the leading coefficient here of that polynomial. It's like a multiplicity, So you end up with a number that by definition is called the F-signature. And just to finish, let me tell you what are the 3 theorems about it. In the notes, you can find the proofs. So I hope that you take your time and you read them. But here's the deal. Theorem 1. Theorem 1. Well, first of all, one has to verify that this number exists, that this limit actually converges. So, well, first of all, definition. This is the F-signature. So first theorem, this thing exists. This converges. And actually, if you think about it, this is a consequence of the subadditivity formula I wrote down for free rank. And a clever argument, that's simple. But it's that subadditivity that magically makes this thing exist. So I encourage you to take a close look into that. So this is theorem 1, theorem 2, which is the easiest of the 3. This thing equals 1, right? This number here is going to be in between 0 and 1. And it could be, it's a real number. Actually, it's an open problem whether or not it's rational, but it's believed not to be. So take this. This happens if and only if. Well, you should know what is the answer, right? Because you know a particular type of rings for which this is going to be 1. Which ones? Regular. Right? Because the sequence is actually constant. It's just 1, 1, 1, 1, 1. But the other direction is it's
because then it's like if the quotient get arbitrarily close to 1,
yeah,
even if they do not become 1,
yeah, they have to be 1.
they have to be 1.
That's the only way, yeah. So actually, yeah, the argument goes as follows. Well, it's in the notes. This part is easy, but yeah, you actually can prove that if these numbers go over a certain threshold, approaching 1, they have to all be 1. So yeah, it's surprising. So one direction is absolutely trivial. Well, it is Kunz. It is as trivial as Kunz's theorem, which is not trivial, but at this point for us, it's a basic thing. The other direction is not so trivial, but it's true. You can read in the notes. And the coolest part of the 3 is that it is positive if and only if R is a regular. So that's another way to think about a signature. So what to say? It means that a regularity just means that you are asymptotically regular as far as Frobenius is concerned. Okay, asymptotically, when you start iterating, the action of Frobenius on R, it's look like asymptotically as a regular ring. Okay, and so here, one direction. Actually, one direction is easier than the other one. This one is easier. If it is positive, it has to be a regular. The other one is a bit harder, but it's true. I'm going to put the both proofs in the notes for you to read. I just would like to finish by saying that there are a ton of open problems about these objects, if you want to work on them. But in general, they all more or less look like this, or are particular cases of the following. Fix K, and look at the K singularities, okay? So here you take, actually as an exercise too, in the notes is that to show that the signature is an invariant under completion. So it's an honest singularity invariant. So look at all K singularities. This just means well, literally just take complete rings, like quotients of this. Okay? Complete local rings with residue field K. That's what a K singularity is. In fixed dimension of dimension D. So I'm going to fix dimension, and I'm going to fix residue field, and therefore characteristic. Okay, and I get a set. This is a set. Because coherent structure theory. It's the same thing as the choice of an ideal of the ring essentially. Essentially, like there are way more ideals than quotient because up to isomorphism, right? Because 2 ideals can give you the same singularity. But whatever, it's a set, and so you can define a signature function to here. And the general open problem in one way or another is what is the structure of this function? Like, is it surjective? We don't know. We don't even have an example of an irrational number, but I expect it to be most of them. So, yeah, what is the structure? So for most singularities, this is going to be 0. So then you can say, okay, let me take the positive one, and then here you're talking about the regular one, right? That's the point. And so, to give me the structure of this map, tell me anything. Essentially, any question you may have about it is open. So,
so would you say we know even less stuff about F signature than about F thresholds or F thresholds?
I would say so, yeah. Anything, just it seems to be a beautiful function. It's a measure of how an irregular ring is, or a ring is, what percentage of it, is regular, so to speak, or actually how percentage it is regular.
Who are the people who came up with this definition, or the first to work with these quotients?
Who were them? This first appeared implicitly in the work of this guy, whose last name is Vandenberg. He works as a Belgian mathematician, and Karen Smith. They were working with these notions of finite representation type and so on. And so they came up implicitly a little with this thing, with these quotients and stuff. And then I think it was Hunike and I believe Aberbach who introduced them, properly speaking. Yeah. And then different people proved these theorems, where the newest one is the existence. Actually, people proved these ones first. Because for a long time, people just worked with, well, okay, if it doesn't exist, we work with the limit and the lim suit. So here you can say, okay, if the lim suit is 0, then blah, blah, blah. Or if the lim if is 1, then blah, blah, blah. But yeah, so I think it's a fascinating invariant. But we don't know much about it.
Yeah, because what I asked you before about the besides like irregularity, if the next thing is regular, that thing is like a slider, like it's one that goes from regularity to regularity, and you can like put almost anything.
Yeah. Yeah, exactly. So for example, what I was telling you is that for example, if there is a threshold here that I forgot that only depends on D and K, so it's an invariant here, such that when you cross it, the signature has to be 1. So there is a gap. Yeah, actually, we know that this is not surjective.
Okay.
Yeah, we know it's not surjective because there is a gap that we never hit. Once we pass the threshold, the value has to be 1. But as we move, actually that thing depends, I think, on P and D. Characteristic and dimension. But that gap, as you increase P and D, both of them approaches 0. Or not both, but either one. If you increase the dimension, it goes to 1. And if you increase P, it goes to 1. Okay? So if you start varying the parameters here, then the signature is surjective. Well, at least that issue doesn't go away. But yeah, that's yeah. But there are types, like Joel Castillo was speaking the other day about like what is the smallest Hilbert-Knudsen multiplicity, right? So same open problem. What is the largest value of? So yeah, and a cool open problem, for example, is what is the largest value besides 1? There is 1. If you fix P and D, there is 1. And this is believed to be the signature of the quadric. Quadric, like taking here to be like you take power series ring and D plus 1 variables, and then you quotient by x, the variables to the square, then the sum of those. At least if the characteristic is not 2, if it's 2, then you have to do a evaluation. But then, like, it is conjecture that that's the largest possible value. But again, like, it's just particular cases of what is the structure of this map in general. But yeah, let's stop here unless you have more questions. Yes, so.